For decades, the existence of dark matter was a conclusion drawn from looking at the sky and seeing a deficit in mass. It was a top-down deduction. We saw a motion, we saw a lack of visible matter, and we filled the gap with a mystery substance. But in the late 20th and early 21st centuries, the search for dark matter moved from the lens of the telescope to the silicon of the supercomputer. This was the era of the in silico universe. Scientists realized that if dark matter were real, they should be able to build a universe from scratch inside a computer, following only the laws of physics, and see if the result matched the real night sky. These simulations, such as the Millennium simulation, the Bolshoi simulation, and more recently the illustrious TNG project, have become the ultimate litmus test for the dark matter hypothesis. They have shown us that without this invisible ingredient, the large-scale structure of the universe, the majestic cosmic web, simply wouldn't exist. To build a universe in a computer, you start at the very beginning, the Big Bang. Cosmologists input the initial conditions observed in the cosmic microwave background, the faint afterglow of the universe when it was only 380,000 years old. These observations show tiny, microscopic ripples in the density of the early universe. In the simulation, the computer is given a recipe for the universe's contents, roughly 5% normal baryonic matter, 27% dark matter, and 68% dark energy. Then the researchers hit the play button and let 13.8 billion years of gravity run forward in time. The computer calculates the gravitational pull between billions of virtual particles, simulating how they clump, merge, and drift across cosmic time. The results are nothing short of a scientific miracle. When dark matter is included in the recipe, the computer generates a structure that is virtually indistinguishable from the maps produced by real-world galaxy surveys like the Sloan Digital Sky Survey. The virtual particles begin to collapse into long, spindly filaments. Where these filaments cross, they form massive, dense nodes. These nodes are where the simulated galaxy clusters form. Between the filaments, the computer produces gargantuan spherical voids where almost no matter exists. This structure, the cosmic web, emerges naturally and inevitably from the influence of dark matter. It proves that dark matter isn't just a fix for a single galaxy's rotation, it is the fundamental blueprint for the entire distribution of matter in existence. However, the real power of these simulations lies in what happens when you remove the dark matter. If you run the same simulation with only the 5% of normal matter we can see, the digital universe fails catastrophically. Normal matter, on its own, is too warm and too easily pushed around by radiation in the early universe. Without the heavy gravitational wells provided by dark matter, the normal gas never has the chance to clump into filaments. The expansion of the universe is too fast. It pulls the matter apart before gravity can gather it into galaxies. In a universe without dark matter, the computer shows a boring, smooth, and featureless fog of gas that expands forever without ever forming a single star. The visible universe we love, the stars, the planets, and the civilizations, is only possible because it is supported by an invisible, massive scaffold that the computer can clearly see, even if our telescopes cannot. This leads to a concept that is critical for understanding why dark matter must be cold. In the world of simulation, there are two competing theories: cold dark matter, CDM, and hot dark matter, HDM. If dark matter were hot, meaning it was made of particles like neutrinos that move at nearly the speed of light, the simulations show a top-down universe. In an HDM universe, massive superclusters form first, and only much later do they fragment into individual galaxies. But when we look through the James Webb Space Telescope at the very early universe, we see the opposite. We see small galaxies forming early and merging into bigger ones. This bottom-up growth is only achieved in simulations where the dark matter is cold. This means the particles must be slow-moving and heavy, allowing them to clump on small scales first. The computer has effectively diagnosed the physical properties of dark matter by testing which versions of the particle produce a universe that looks like ours. The precision of these simulations has reached a point where they can even simulate the baryonic feedback, the way stars and supernovae affect the dark matter. For a long time, there was a discrepancy known as the core cusp problem. Simple dark matter simulations predicted that the centers of galaxies should be incredibly dense with dark matter, a cusp, but observations of real galaxies showed a smoother, flatter distribution, a core. Skeptics use this to argue that dark matter wasn't real, but when modern supercomputers, like the ones used for the Fire and Eagle simulations, began to include the violent effects of exploding stars, the problem was solved. They showed that when massive stars explode, they push the normal gas out of the galaxy's center. This sudden shift in mass causes the gravitational field to vibrate, which in turn stirs the dark matter and pushes it outward, smoothing the cusp into a core. The simulation didn't just match the large-scale web, it explained the subtle, small-scale anomalies that had baffled astronomers for years. Furthermore, these simulations provide a bridge to gravitational lensing studies. By simulating how light travels through the virtual cosmic web, researchers can predict exactly how much distortion we should see when looking at distant galaxies. They can create virtual lensing maps and compare them to the real data from missions like Euclid. The agreement is staggering. The gravitational topography predicted by the dark matter scaffolding matches the lensing topography measured in the real sky down to the smallest detail. This cross-verification between digital models and physical observations is why the scientific community is so confident in the dark matter model. It's no longer just an idea, it's a predictive tool that works across trillions of miles and billions of years. The scale of these simulations is helping us understand the dark sector as a whole. By tweaking the amounts of dark matter and dark energy in the computer, we can see how they tug against each other. Dark matter wants to pull the universe into a tight web, dark energy wants to rip that web apart. By comparing the clumpiness of the virtual universe with the real sky, we can measure the exact ratio of these two forces. This has led to the standard model of cosmology, known as the Lambda CDM model. It is the definitive rule book for the universe, and its most important chapter is the one written in the language of dark matter. As we look at the breathtaking visualizations produced by these supercomputers, we're forced to see the universe as an organic, growing thing. We see the dark matter filaments pulsing and growing like the neural networks of a giant brain. We see the galaxies as tiny synapses firing at the intersections of these invisible nerves. The simulation teaches us that the unseen architecture is not just a passive framework, it is a dynamic, living system that is still evolving. The cosmic web we see today is much clumpier than it was 10 billion years ago, and it will be even more defined 10 billion years from now as dark matter continues its slow, relentless work of gathering the universe together. The success of these simulations is the ultimate rebuttal to those who believe dark matter is just a math trick. A math trick wouldn't consistently recreate the intricate, fractal-like structure of the cosmic web across every scale, from the tiniest dwarf galaxy to the largest supercluster. A math trick wouldn't predict the subtle gaps in stellar streams or the precise temperature of the intergalactic gas. The computer is telling us a truth that our eyes are too limited to see. We are living in a dark matter universe, and the starlight is just the ink that makes the invisible blueprint visible. In conclusion, supercomputer simulations have moved dark matter from the realm of missing mass to the realm of predictive science. They have proven that the cosmic web is the inevitable outcome of a dark matter-dominated universe. They have given us a map of the invisible, allowing us to navigate the vast distances of the cosmos with a level of detail that would have been impossible just a generation ago. In the next chapter, we will look at the simulations that fail and why a universe without dark matter is a universe that could never produce life.
In the high-stakes world of modern cosmology, the most powerful tool for truth isn't always the telescope, it is the delete key. To prove that dark matter is an essential component of reality, scientists have spent thousands of hours of supercomputer processing time doing something seemingly counterintuitive. They have tried to build universes without it. These are called baryon-only simulations. In these digital experiments, researchers strip away the dark matter and attempt to create a cosmos using only the normal matter we find in the periodic table, the protons, neutrons, and electrons that make up stars, planets, and people. The results of these failed universes are the most haunting and definitive evidence we have. Without dark matter, the universe as we know it simply refuses to form. The majestic patterns of galaxy clustering that define our night sky evaporate into a featureless, chaotic mist. To understand why a dark matter-free universe fails, we have to look at the clumping problem. In the immediate aftermath of the Big Bang, the universe was expanding at a staggering rate. At the same time, gravity was trying to pull matter together to form the first structures. It was a race against time. If gravity didn't win quickly enough, the expansion of space would push the atoms so far apart that they could never meet. In a universe containing only normal matter, gravity is a weak contender. Normal matter is baryonic, meaning it interacts with light and radiation. In the early universe, this radiation was so intense that it acted like a high-pressure wind. Every time a cloud of hydrogen gas tried to collapse into a star, the radiation pressure pushed it back out. This created a state of silk damping, where the ripples of the early universe were effectively washed away. When we run these baryon-only simulations on supercomputers, like those at the NASA Advanced Supercomputing Division, we see this process play out in real time. Without the extra gravity of dark matter to act as an anchor, the normal matter is too slippery to settle down. The simulated universe expands for hundreds of millions of years, but the first stars never ignite. The gas remains diffuse, spread out in a thin, uniform fog. By the time the radiation pressure finally subsides, the expansion of the universe is already won. The distance between gas particles has become so great that their mutual gravitational pull is too weak to overcome the Hubble flow. In these digital voids, there are no galaxies, there is no Milky Way. There is only a dark, cold, and lonely expansion of gas that never realizes its potential to become something more. The failure of these simulations becomes even more glaring when we look at large-scale clustering. In our real universe, galaxies are not distributed randomly. They follow the cosmic web architecture we discussed in previous chapters, grouping into long filaments and massive clusters. This clustering has a specific scale to it. There is a mathematical relationship between how many small galaxies exist compared to large ones. When we look at the results of a simulation without dark matter, this clustering is non-existent. The power spectrum of the universe, the measure of how much stuff is clumped at different sizes, comes out completely wrong. It would be like trying to bake a loaf of bread without yeast. You have the flour, normal matter, and the water, gravity, but without the yeast, dark matter, the bread never rises. It remains a flat, dense, and useless slab. This clustering deficit is why the dark matter hypothesis is so robust. It isn't just a math trick to fix a single problem. It is the only way to get the entire distribution of the universe to match. Skeptics of dark matter often point to modified Newtonian dynamics, MOND, as an alternative. MOND suggests that we don't need dark matter if we simply change the laws of gravity at low accelerations. However, when MOND is plugged into these large-scale simulations, it fails to recreate the cosmic web. While MOND can be tuned to make a single galaxy spin correctly, it cannot explain why the galaxies are arranged in a web-like pattern across billions of light years. The simulations show that the shape of the universe is a physical consequence of a heavy, invisible substance pulling on the visible world. You cannot math your way out of the need for a physical scaffolding. Furthermore, simulations without dark matter struggle with the timing of the universe. One of the most shocking discoveries from the James Webb Space Telescope is the presence of massive early galaxies. We are seeing fully formed, mature galaxies in a universe that was only 500 million years old.
This is a massive headache for baryon-only models. Without the extra gravity of dark matter to act as an anchor, the normal matter is too slippery to settle down. The simulated universe expands for hundreds of millions of years, but the first stars never ignite. The gas remains diffuse, spread out in a thin, uniform fog. By the time the radiation pressure finally subsides, the expansion of the universe has already won. The distance between gas particles has become so great that their mutual gravitational pull is too weak to overcome the Hubble flow. In these digital voids, there are no galaxies, there is no Milky Way. There is only a dark, cold, and lonely expansion of gas that never realizes its potential to become something more. The failure of these simulations becomes even more glaring when we look at large-scale clustering. In our real universe, galaxies are not distributed randomly. They follow the cosmic web architecture we discussed in previous chapters, grouping into long filaments and massive clusters. This clustering has a specific scale to it. There is a mathematical relationship between how many small galaxies exist compared to large ones. When we look at the results of a simulation without dark matter, this clustering is non-existent. The power spectrum of the universe, the measure of how much stuff is clumped at different sizes, comes out completely wrong. It would be like trying to bake a loaf of bread without yeast. You have the flour, normal matter, and the water, gravity, but without the yeast, dark matter, the bread never rises. It remains a flat, dense, and useless slab. This clustering deficit is why the dark matter hypothesis is so robust. It isn't just a math trick to fix a single problem. It is the only way to get the entire distribution of the universe to match. Skeptics of dark matter often point to modified Newtonian dynamics, MOND, as an alternative. MOND suggests that we don't need dark matter if we simply change the laws of gravity at low accelerations. However, when MOND is plugged into these large-scale simulations, it fails to recreate the cosmic web. While MOND can be tuned to make a single galaxy spin correctly, it cannot explain why the galaxies are arranged in a web-like pattern across billions of light-years. The simulations show that the shape of the universe is a physical consequence of a heavy, invisible substance pulling on the visible world. You cannot math your way out of the need for a physical scaffolding. Furthermore, simulations without dark matter struggle with the timing of the universe. One of the most shocking discoveries from the James Webb Space Telescope is the presence of massive early galaxies. We are seeing fully formed, mature galaxies in a universe that was only 500 million years old. This is a massive headache for baryon-only models. Without the extra gravity of dark matter to act as an anchor, the normal matter is too slippery to settle down. The simulated universe expands for hundreds of millions of years, but the first stars never ignite. The gas remains diffuse, spread out in a thin, uniform fog. By the time the radiation pressure finally subsides, the expansion of the universe has already won. The distance between gas particles has become so great that their mutual gravitational pull is too weak to overcome the Hubble flow. In these digital voids, there are no galaxies, there is no Milky Way. There is only a dark, cold, and lonely expansion of gas that never realizes its potential to become something more. The failure of these simulations becomes even more glaring when we look at large-scale clustering. In our real universe, galaxies are not distributed randomly. They follow the cosmic web architecture we discussed in previous chapters, grouping into long filaments and massive clusters. This clustering has a specific scale to it. There is a mathematical relationship between how many small galaxies exist compared to large ones. When we look at the results of a simulation without dark matter, this clustering is non-existent. The power spectrum of the universe, the measure of how much stuff is clumped at different sizes, comes out completely wrong. It would be like trying to bake a loaf of bread without yeast. You have the flour, normal matter, and the water, gravity, but without the yeast, dark matter, the bread never rises. It remains a flat, dense, and useless slab. This clustering deficit is why the dark matter hypothesis is so robust. It isn't just a math trick to fix a single problem. It is the only way to get the entire distribution of the universe to match. Skeptics of dark matter often point to modified Newtonian dynamics, MOND, as an alternative. MOND suggests that we don't need dark matter if we simply change the laws of gravity at low accelerations. However, when MOND is plugged into these large-scale simulations, it fails to recreate the cosmic web. While MOND can be tuned to make a single galaxy spin correctly, it cannot explain why the galaxies are arranged in a web-like pattern across billions of light-years. The simulations show that the shape of the universe is a physical consequence of a heavy, invisible substance pulling on the visible world. You cannot math your way out of the need for a physical scaffolding. Furthermore, simulations without dark matter struggle with the timing of the universe. One of the most shocking
In the world of human perception, seeing is believing. Our entire evolutionary history has been a masterclass in interpreting the electromagnetic spectrum. We rely on photons, tiny packets of light, to bounce off objects and hit our retinas, allowing us to build a mental map of reality. If something doesn't reflect light, we assume it is nothing. But in the vast theater of the cosmos, light is a secondary player. The true currency of the universe is not light, it is gravity. Gravity is the only force that cares about the total content of the universe. It doesn't care if you are a bright star, a cold planet, a black hole, or a ghost-like particle of dark matter. If you have mass, you have a gravitational footprint. This chapter explores the profound reality that while dark matter remains invisible to every camera ever built, it is heavy in a way that makes it impossible to hide. To understand how we weigh the invisible, we have to look back at Albert Einstein's greatest gift to humanity, general relativity. Einstein taught us that gravity is not a mysterious force that pulls things through space. Rather, it is the very shape of space itself. Imagine a trampoline stretched tight. If you place a bowling ball in the center, the fabric curves. If you roll a marble across the trampoline, it follows the curve. In this analogy, the bowling ball doesn't need to glow for you to know it's there. You could be blindfolded and still know exactly where the ball is, how much it weighs, and how large it is, simply by feeling the curve of the fabric with your hands. This is exactly how modern astronomers weigh dark matter. We look at the curves in space-time, the gravitational wells, and we calculate how much mass must be sitting at the bottom of them to create that specific shape. This method of gravitational weighing is the bedrock of our certainty. It relies on the equivalence principle, which suggests that all mass, regardless of its chemical composition, responds to gravity in the same way. Whether you are made of gold, hydrogen, or dark matter, you will create a dent in space-time proportional to your mass. This allows us to perform cosmic bookkeeping. We can look at a region of space, measure the total curvature, the gravity, and then count up all the visible objects that could be causing that curvature. When we find that the space is warped 5 times more than the visible stars can account for, we aren't guessing that something is there. We are measuring a physical reality. The dent in the universe is real, even if the object sitting in it is invisible. One of our most precise weighing scales is gravitational lensing. As light travels across the universe, it must follow the trampoline curves of space-time. If a massive clump of dark matter sits between us and a distant galaxy, the light from that galaxy will be bent, stretched, and magnified as it passes through the dark matter's gravitational well. This creates Einstein rings, or long luminous arcs. By using complex algorithms to undistort these images, astronomers can create a high-resolution map of the mass that caused the bending. These maps are the fingerprints of dark matter. We can see exactly where the mass is lumpy and where it is smooth. In many cases, these lensing maps reveal massive peaks of gravity in areas where there is absolutely no starlight. We're effectively seeing the weight of the dark architecture through the warped light of the distant background. But we don't just weigh dark matter through lensing, we also weigh it through orbital dynamics. Every object in the universe is in a state of falling. The Earth is falling around the Sun is falling around the center of the Milky Way. Galaxies are falling toward each other in clusters. By measuring the orbital velocity, how fast these objects are falling, we can determine the total mass of the system they're falling into. This is the same math that allowed us to discover Neptune before we ever saw it with a telescope. We saw Uranus wobbling in its orbit, and we calculated that there had to be another planet further out pulling on it. We didn't need to see Neptune's blue surface to know it was there. We could weigh its influence. Dark matter is the ultimate Neptune. Its influence is felt in every orbital wobble of every star in the sky. This weighing also happens on the scale of the intra-cluster medium. As we discussed in earlier chapters, galaxy clusters are filled with superheated gas. This gas is so hot that it should have evaporated into space long ago. The only reason it stays trapped is the gravitational pressure of the dark matter. By measuring the temperature and pressure of this gas using X-ray telescopes like Chandra or XMM Newton, we can calculate the escape velocity of the cluster. If the gas is 10 million degrees, it's moving at millions of miles per hour. To hold on to something moving that fast, you need a specific amount of mass. When we run the numbers, the visible mass, stars and gas, only provides about 15% of the necessary grip. The other 85% must be the dark matter. We are weighing the dark matter by measuring the heat of the normal matter it is crushing. Why is this indirect weighing so reliable? Because it comes from multiple independent lines of evidence that all point to the same number. If we only had galaxy rotation curves, we might think we just misunderstood how stars move. If we only had lensing, we might think we misunderstood how light travels. If we only had X-ray gas, we might think we misunderstood how heat works. But when the rotation weight, the lensing weight, and the gas pressure weight all give us the exact same answer, that the universe is 85% dark, the margin of error disappears. It is a triple point of scientific proof. It's like 3 different people weighing a box on 3 different scales in 3 different rooms, and everyone getting the same result. The weight is a physical fact. This brings us to the mass-to-light ratio, m/L. In the solar system, the m/L ratio is 1, using the sun as the standard. For every unit of light, there is 1 unit of mass. In a typical galaxy, the m/L ratio is closer to 50 or 100. For every 1 unit of light we see, there are 100 units of mass present. In some extreme cases, like the ultra-diffuse galaxies, the m/L ratio can be as high as 1,000. These are essentially dark matter galaxies that have almost no stars at all. They are all weight and no light. If we didn't have the ability to weigh them via gravity, we would never even know they existed. They would be the ultimate ghost galaxies, drifting through the void, massive and silent, invisible to every sensor but the sensor of gravity itself. As we look toward the future, our cosmic scales are getting even more precise. The Euclid mission and the Nancy Grace Roman telescope are designed to perform weak lensing surveys on a scale never before attempted. They will measure the shapes of billions of galaxies across 10 billion years of cosmic history. This will allow us to see how the weight of the universe has shifted and moved over time. We will be able to watch the dark matter scaffolding clump as gravity pulls it together. We are moving from simply weighing the dark matter to filming it. We are watching the invisible architect at work by tracking the way it bends the light of the entire sky. In conclusion, the fact that we cannot see dark matter is a limitation of our eyes, not a limitation of our science. By using gravity as our universal translator, we have turned the entire universe into a scale. We have measured the invisible, and we have found that it is the dominant player in the cosmic story. Starlight is just the decoration on the scale. The dark matter is the load. Every time you see a beautiful picture of a galaxy, remember that you are only seeing the tiny percentage of matter that was lucky enough to interact with light. The rest of the galaxy, the heavy part, is hiding in the shadows, revealing itself only through the quiet, relentless pull of its gravity.
In the standard visualization of a galaxy, we focus on the luminous spiral, the brilliant flat disk of stars and gas that gives a system like the Milky Way its iconic shape. However, this is a perspective born of our limited biological senses. In the true gravitational reality of the universe, a galaxy is not a disk, it is a sphere. Every shining galaxy we observe is merely the bright central seed inhabiting a much larger invisible environment known as a dark matter halo. These halos are the true gravitational homes of the universe, providing the structural foundation and the protective cocoon that allows galaxies to assemble, grow, and persist over billions of years. To understand the life of a galaxy, one must first understand the vast dark architecture that encloses it. The concept of the galactic halo fundamentally shifts our understanding of where a galaxy ends. While the visible stars of the Milky Way might stretch out to a radius of about 50,000 light-years, the dark matter halo extends far beyond that, reaching out nearly 1,000,000 light-years into the intergalactic void. If you were to look at the Milky Way with gravity eyes, the familiar spiral would appear as a tiny glowing pearl at the center of a gargantuan invisible beach ball. This halo is not just a passive container, it is an active participant in the galaxy's evolution. It acts as a deep gravitational basin that catches the normal matter, the hydrogen and helium gas, and pulls it inward until it is dense enough to ignite into stars. Without the pre-existing dark matter halo to provide this nest, the gas would remain too diffuse to ever form a structured galaxy. Evidence for these vast halos comes from the motion of satellite galaxies. The Milky Way is surrounded by dozens of smaller companions, such as the Large and Small Magellanic Clouds and numerous ultra-faint dwarf galaxies. For years, astronomers were puzzled by why these satellites remained in such tight orbits. Based on the visible mass of the stars in our galaxy, these companions should have moved with much greater freedom or escaped altogether. Instead, they move through the outskirts of our system as if they are riding on invisible currents within a massive, heavy ocean. By tracking the three-dimensional orbits of these satellites using missions like Gaia, we can feel out the shape and extent of the dark matter halo. We find that the halo is roughly spherical, though slightly stretched, triaxial, and it provides a consistent gravitational pull that keeps our satellite family close. The halo is also the site of one of the most violent and important processes in galactic life, accretion. Because the dark matter halo is so massive, its gravity is constantly pulling in smaller clumps of matter from the surrounding space. These can be small clouds of gas or even entire dwarf galaxies. As these objects fall into the halo, they are subjected to tidal forces. The side of the object closer to the center of the Milky Way is pulled harder than the far side, stretching the object into a long, thin ribbon of stars known as a stellar stream. We have discovered dozens of these streams wrapping around the Milky Way like silver threads on a loom. These streams are the fossil records of our galaxy's growth. By studying their paths, we can reconstruct the density and distribution of the dark matter they are traveling through. If the dark matter halo were smooth, the streams would be uniform. If the halo is lumpy with smaller subhalos of dark matter, the streams develop gaps and kinks. This brings us to the substructure of the halo. Simple models of cold dark matter, CDM, predict that the massive halo of a galaxy shouldn't be a smooth, featureless cloud. Instead, it should be bumpy, containing thousands of smaller subhalos. These are essentially mini-halos of dark matter that were captured by the larger galaxy but haven't yet merged into the core. Some of these subhalos contain stars, which we see as dwarf galaxies, but most of them are believed to be dark satellites, clumps of mass that have no stars at all. These dark satellites are the stealth bombers of the halo. They roam the outskirts of the Milky Way, invisible to our telescopes, yet their gravity can perturb the orbits of stars and influence the stability of the galactic disk. The search for these dark subhalos is one of the critical tests of our dark matter theories. If we find too many or too few, we may have to rethink the very nature of the dark matter particle. The interaction between the halo and the visible disk is also responsible for the stability of the galaxy. Spiral disks are inherently unstable. Without an external influence, they tend to develop massive bars in their centers or buckle into chaotic shapes. The presence of a massive dark matter halo provides a gravitational floor that stabilizes the disk, allowing it to maintain its spiral arms for billions of years. The halo acts like the heavy ballast at the bottom of a sailboat, preventing the galaxy from capsizing during encounters with other systems. Furthermore, the halo influences the galactic fountain, the process where hot gas is blown out of the disk by supernovae and eventually cools and falls back in. The halo acts as a gas reservoir, catching this material and recycling it back into the disk to form new generations of stars. When galaxies collide, it's the halos that meet first. In the impending collision between the Milky Way and the Andromeda Galaxy, our dark matter halos are already beginning to overlap. As these two massive structures pass one another through, they experience dynamic friction. Imagine a heavy ball moving through a sea of smaller particles. The ball pulls the particles toward it, creating a wake of mass behind it. This wake then pulls back on the ball, slowing it down. This is exactly how dark matter halos interact. The friction generated by the overlapping halos will gradually slow down the Milky Way and Andromeda, stripping them of their orbital energy and dragging them together into a final, permanent merger. The invisible architecture is the brake of the universe, ensuring that these massive systems don't just zip past each other, but eventually unite to form a single elliptical giant. This halo-driven merger also explains the separation of mass seen in systems like the Bullet Cluster. When two galaxy clusters collide, the hot gas, normal matter, crashes together and slows down due to electromagnetic pressure, but the galaxies and the dark matter mostly pass right through one another. This is because dark matter is collisionless. It doesn't bump into things. The dark matter halos simply glide through the encounter, following their original paths while the normal gas gets stuck in the middle. By using gravitational lensing, we can see the dark matter halos slipping ahead of the glowing gas. This is perhaps the most vivid demonstration of the halo's reality. We can see the ghost of the galaxy's mass moving independently of its visible body. The density profile of these halos is also a subject of intense scientific debate. Standard simulations suggest that halos should have a cusp, a sharp increase in density toward the very center. However, when we look at dwarf galaxies, we often find a core, a flatter, more uniform distribution of mass. This is the core cusp problem. One explanation is stellar feedback. The violent energy of exploding stars in the galactic center might stir the dark matter, pushing it outward and smoothing the cusp into a core. Another possibility is that dark matter isn't perfectly collisionless. Perhaps the particles can bounce off one another slightly, self-interacting dark matter, which would naturally create a smoother core. The shape of the halo, therefore, is a crime scene that tells us about the internal physics of the dark matter particle. As we conclude our journey through the galactic halo, we must realize that we are the inhabitants of this invisible structure. Every star you see at night is tethered to the Milky Way by the invisible thread of the dark matter halo. We are the light that reveals the dark. Without the halo, there would be no disk, no sun, and no Earth. The halo is the ultimate macro-architecture, the silent guardian that has allowed the complexity of the visible world to flourish. In the next chapter, we will look at how these massive halos were first caught in the act of colliding, revealing the shadow of gravity in a way that light never could.
In the search for dark matter, scientists often look for a smoking gun, a single, definitive observation that proves beyond a shadow of a doubt that dark matter is a physical substance and not just a misunderstanding of the laws of gravity. While the rotation of galaxies and the clustering of the cosmic web are compelling, they rely on systems that are in a state of equilibrium. To truly isolate the invisible from the visible, we need to witness a catastrophe. We need to see what happens when the universe's largest structures crash into one another at millions of miles per hour. This brings us to the study of colliding galaxy clusters, specifically the iconic Bullet Cluster. These cosmic traffic accidents provide a natural experiment on a scale so grand that they allow us to see the shadow of gravity physically separating from the glowing matter we call home. To understand the significance of these collisions, we must first analyze the three main components of a galaxy cluster.
First, there are the galaxies themselves, shining islands of stars that, surprisingly, make up only about 1 to 2% of the cluster's total mass. Second, there is the intracluster medium, a vast sea of superheated gas that fills the space between galaxies. This gas is much more substantial than the stars, accounting for about 10 to 15% of the mass. Finally, there is the dark matter, which makes up the remaining 85%. In a normal, resting cluster, these three ingredients are all piled on top of each other in a single gravitational well. But when two clusters collide, their different physical properties cause them to separate, like oil and water being shaken in a bottle. The physics of a cluster collision is a study in collisionality. When two clusters meet, the galaxies within them rarely ever collide. Because the distances between stars are so vast, the galaxies simply pass through each other like two swarms of bees crossing paths. They are collisionless because they are mostly empty space. Dark matter, according to our leading theories, is also collisionless. It does not feel the electromagnetic force, meaning dark matter particles from one cluster don't bump into dark matter particles from the other. They glide right through the impact zone, unaffected by the violence of the encounter. However, the hot gas behaves very differently. The gas is a fluid composed of charged particles, plasma. When the gas cloud of one cluster hits the gas cloud of another, they experience immense ram pressure and electromagnetic resistance. They don't pass through, they crash, heat up even further, and get stuck in the middle of the collision site. This creates a spectacular separation. In the aftermath of the crash, the normal matter, the gas, is left behind in the center of the wreckage, while the dark matter, the gravity, and the galaxy sail onward, unbothered by the friction. The bullet cluster, officially known as 1E0657558-, is the most famous example of this phenomenon. Using NASA's Chandra X-ray Observatory, astronomers mapped the location of the hot gas and found it shaped like a bullet with a prominent shock front, located squarely in the center of the collision. Then, using the Hubble Space Telescope, they performed a gravitational lensing analysis. They looked at how the light from distant background galaxies was bent as it passed through the cluster. This allowed them to map exactly where the mass of the cluster was located. The result was the most significant discovery in the history of dark matter research. The map of the mass, the gravity, did not line up with the map of the gas. The vast majority of the cluster's weight had slipped ahead of the gas. It was sitting in empty space, surrounding the galaxies that had passed through the impact. This was the smoking gun. If dark matter were just a misunderstanding of gravity, the gravity should always be centered where the most visible matter, the gas, is located. But in the bullet cluster, the gravity and the matter are in two different places. This proves that the gravity is being generated by a physical, invisible substance that is capable of moving independently from the atoms we can see. This separation of mass provides a powerful rebuttal to theories of modified gravity. While modified gravity can explain why a single galaxy rotates strangely, it struggles to explain how gravity can literally detach itself from the matter that supposedly generates it. In the bullet cluster, we see a shadow of gravity that has been stripped away from its gaseous body. This only makes sense if dark matter is a real, non-baryonic particle that does not feel the friction of normal matter. The bullet cluster turned dark matter from a theoretical fix into a tangible reality. Since the discovery of the bullet cluster, astronomers have found dozens of other merging clusters that show similar effects, such as the Trainwreck cluster, Abell 520, and the Musketball cluster. Each of these provides a different perspective on the collision. Some show the dark matter behaving perfectly as expected, while others, like the Trainwreck cluster, show more complex patterns that suggest we might still have things to learn about how dark matter clumps during violent encounters. These systems act as cosmic particle accelerators, allowing us to study the self-interaction of dark matter. If dark matter particles could bounce off one another, we would see the dark matter halos slump or slow down slightly during the collision. By measuring the exact offset between the galaxies and the dark matter, we can place strict limits on how much dark matter feels itself. The study of these collisions reveals the history of structure.
When clusters collide, they trigger massive waves of star formation in the member galaxies as gas is compressed and stirred. However, the dark matter halos remain the silent overseer of the process. Even as the gas is glowing and the stars are exploding, the dark matter halos are already beginning to pull the system back together. Over the next few billion years, the friction of the dark matter halos, dynamical friction, will eventually slow the clusters down enough that they will fall back toward the center and merge into a single, massive, relaxed cluster. The accident is temporary. The dark matter's gravitational will is permanent. Furthermore, these colliding systems allow us to test the dark sector beyond just mass. Some theories suggest that dark matter might be governed by its own dark forces, a dark version of electromagnetism that we cannot see. If these forces existed, we would see them in the way the dark matter halos deform during a collision. So far, the evidence suggests that dark matter is remarkably boring. It seems to only care about gravity. It passes through itself and through normal matter with almost perfect transparency. This collisionless nature is a vital clue for particle physicists. It tells them that whatever the dark matter particle is, it must be extremely antisocial, avoiding all interactions except for the cosmic tug-of-war. The implications of these collisions reach down to the very definition of reality. They teach us that our visible world is a fragile, high-friction environment, while the dark world is a streamlined, effortless majority. We are the gas that gets stuck in the middle, glowing with heat and energy, while the dark matter is the silent traveler that carries the true momentum of the universe. The bullet cluster is a reminder that what we see is often the most chaotic and least important part of the story. The real power, the mass that defines the paths of galaxies, is moving in the silence, invisible even during the most violent events in the cosmos. As we look at these cosmic wrecks, we are effectively seeing the universe unmasked. For a brief moment during a collision, the dark matter and the normal matter are pulled apart, allowing us to see each one for what it truly is. We see the gas for its pressure and light, and we see the dark matter for its pure, unadulterated gravity. This separation is the cornerstone of our modern standard model of cosmology. It proves that we are living in a multi-component universe where the visible and the invisible play by different rules but are forever bound by the same curvature of space. In conclusion, colliding galaxy clusters are the ultimate proof of dark matter's physical reality. They provide a visual and mathematical demonstration that gravity is not always where the light is. They show us that the unseen architecture can be stripped of its visible decorations and still maintain its form. The bullet cluster isn't just a discovery, it is a profound shift in our cosmic perspective. In the next chapter, we will look at how this shadow of gravity does more than just hold things together. It also acts as a cosmic magnifying glass that allows us to see the farthest reaches of the universe.
In the profound darkness of deep space, gravity does more than just pull. It sculpts the very path of light itself. This phenomenon, known as gravitational lensing, is perhaps the most visually arresting evidence for the unseen architecture of the universe. When we peer through our most powerful telescopes, we often see galaxies that appear strangely distorted, stretched into long, luminous arcs, smeared into circles, or even appearing in multiple places at once, like a celestial hall of mirrors. These are not optical illusions caused by the telescope's lens, nor are they the result of atmospheric interference. They are the direct consequence of massive concentrations of dark matter warping the fabric of space-time. By acting as a cosmic magnifying glass, dark matter allows us to see the weight of the invisible, while simultaneously providing us with a telescope that reaches further than any human-made instrument ever could. The physics behind this effect is rooted in Albert Einstein's general theory of relativity. Einstein proposed that mass does not simply exist in space, it defines the shape of space. A massive object, like a galaxy cluster dominated by dark matter, creates a dent or a curvature in the four-dimensional fabric of spacetime. When light from a more distant background galaxy travels toward Earth, it must follow the contours of this curved space. As the light passes the massive foreground object, its path is bent, much like light passing through a glass lens. If the foreground mass is large enough and the alignment is precise, the light is focused and magnified, allowing us to observe ancient galaxies that would otherwise be far too faint and distant to detect. Crucially, gravitational lensing is mass blind. Unlike a star, which we see because of its light, or a gas cloud, which we detect through its heat, a gravitational lens responds to total mass. It doesn't care if that mass is made of glowing atoms or invisible dark matter. This makes lensing the ultimate tool for weighing the dark sector. When astronomers analyze a lensing system, they calculate how much mass is required to create the specific distortions seen in the image. Time and again, the results show a massive deficit. The visible stars and gas in the foreground lens are only a small fraction of what is needed to bend the light so severely. In most cases, there must be 5 to 10 times more invisible matter than visible matter to account for the arcs and rings we observe. We are literally using the distorted light of the distant universe to map the shadows of the dark matter in front of it. There are 3 primary types of gravitational lensing that dark matter facilitates, each providing a different zoom into the dark universe. The first is strong lensing, which occurs in the dense cores of galaxy clusters. Here, the gravity is so intense that it produces dramatic, easily visible distortions. We see Einstein rings, where a background galaxy is stretched into a perfect circle around the foreground mass. We also see multiple images, where a single background quasar or galaxy appears 4 or 5 times in a cross-like pattern around the lens. By studying these systems, we can map the cuspiness of dark matter, how tightly it piles up in the centers of galaxies. This is a vital test for particle physics. If dark matter particles can interact with each other, they would puff up the center, changing the shape of the lensing distortions. The second type is weak lensing, which is more subtle but arguably more powerful for mapping the large-scale structure of the cosmos. In weak lensing, the light is not stretched into dramatic arcs. Instead, millions of distant galaxies are slightly nudged or tilted in their orientation. By itself, the distortion of a single galaxy is too small to measure reliably, but when astronomers use supercomputers to analyze the shapes of millions of galaxies across a wide patch of sky, a pattern emerges. They find that the galaxies are all slightly aligned toward invisible concentrations of mass. This allows us to map the cosmic web of dark matter that we discussed in earlier chapters. Weak lensing is our primary way of seeing the connective tissue of the universe, the invisible bridges of dark matter that span the voids between galaxy clusters. The third type is microlensing, which happens on much smaller scales. This occurs when a compact object, like a dark matter clump or a rogue planet, passes directly in front of a distant star. The gravity of the small object briefly magnifies the star's light, causing it to brighten and then fade in a very specific way. In the 1990s, projects like Macho and Eros used microlensing to search for compact dark matter, the idea that dark matter might just be millions of dead stars or black holes. However, these surveys found very few events, effectively proving that dark matter isn't made of normal heavy objects like planets or burnt-out suns. It must be something more exotic, like a diffuse cloud of subatomic particles. Microlensing helped us rule out the obvious and forced us to look toward the quantum world for answers. One of the most spectacular applications of dark matter lensing is using it as a natural telescope. Because gravitational lensing magnifies distant objects, it allows us to see galaxies that existed just a few 100 million years after the Big Bang. These high redshift galaxies are normally invisible even to the James Webb Telescope, but when a massive dark matter cluster acts as a lens, it can magnify these ancient objects by a factor of 10, 50, or even 100. This has led to the discovery of Arundel, the most distant individual star ever seen, which was only visible because it was perfectly aligned with a ripple in the dark matter lens of a foreground cluster. Dark matter isn't just a mystery to be solved, it is a tool that we use to explore the deepest history of the cosmos. Furthermore, lensing allows us to measure the expansion rate of the universe, the Hubble constant.
In systems with multiple images of the same background quasar, the light for each image takes a slightly different path and arrives at a slightly different time. If the background quasar flickers, we see that flicker in the first image, then minutes or days later in the second, third, and fourth images. These time delays are directly related to the mass of the dark matter lens and the geometry of the expanding universe. It is a completely independent way of measuring how fast space is growing, providing a crucial check on other methods like supernova measurements or the cosmic microwave background. The beauty of gravitational lensing is that it provides a purely geometric proof of dark matter. It doesn't rely on complex assumptions about how gas cools or how stars evolve. It simply relies on the fact that mass bends space. When we see a dark lens, a region of space that bends light but contains no stars, we are seeing dark matter in its purest form. We are seeing a gravitational ghost that has no body of light but possesses a massive weight of influence. This phenomenon turns the entire universe into a laboratory for general relativity, with dark matter acting as the primary substance that gives the lab its shape. As we conclude this chapter, consider the sheer elegance of this cosmic arrangement. The very substance that makes up the majority of the universe's mass, yet remains invisible to our eyes, has provided us with the lenses we need to see further into the darkness. Dark matter creates the curvature, and that curvature directs the light. We are like sailors navigating a dark sea, using the swells and waves in the water to understand the deep currents that move beneath us. Gravitational lensing is the wake of the dark matter, and by studying that wake, we have begun to chart the invisible map of the heavens. In the final chapter, we will synthesize all we have learned. We will look at how this unseen architecture, this rotating puzzle, this cosmic web, and these gravitational lenses all point toward a single unified truth. We live in a dark universe, and the time for its discovery is now. We will look at the next generation of experiments, from deep underground detectors to space-based observatories that are finally closing in on the identity of the dark matter particle.
As we reach the final frontier of our journey through the unseen architecture of the cosmos, we move from the gargantuan scales of galaxy clusters and the cosmic web down into the subatomic realm. We have seen the crimes of dark matter, the way it tugs on stars, warps the path of light, and builds the scaffolding of the universe. We have measured its weight and mapped its distribution, but the ultimate question remains: what is it? If dark matter is a physical substance, it must be composed of something. However, every time we look at the periodic table, the glorious catalog of every element known to man, we find that dark matter simply doesn't fit. It isn't hydrogen, it isn't carbon, and it isn't iron. It is a ghost in the machine, a new kind of particle that exists outside the standard model of physics. This final chapter explores the leading candidates for the dark matter particle and the extraordinary experiments currently underway to catch a ghost. The fundamental mystery of the dark matter particle is its antisocial nature. In our daily lives, we are used to matter that interacts. When you touch a table, your hand doesn't pass through it because the electromagnetic forces in your atoms repel the electromagnetic forces in the table's atoms. When light hits an object, it bounces off or is absorbed. This is how we perceive the world. But dark matter is collisionless. It possesses mass, so it feels the pull of gravity, but it appears to be entirely deaf to the electromagnetic force and the strong nuclear force. This means a dark matter particle could fly through a lead wall a light-year thick and never slow down. It could stream through your body, through the Earth's core and out the other side, without ever touching a single atom. To understand such a particle, we have to look for candidates that barely touch our reality. The leading candidate for decades has been the WIMP, or Weakly Interacting Massive Particle. The beauty of the WIMP hypothesis lies in what physicists call the WIMP miracle.
When researchers calculated how much of a heavy, weakly interacting particle would have survived from the heat of the Big Bang, the number matched the amount of dark matter we see in the universe today almost perfectly. WIMPs are theorized to be about 10 to 1,000 times heavier than a proton, but they only interact via gravity and the weak nuclear force, the force responsible for radioactive decay. To catch a WIMP, scientists have built some of the silentest places on Earth. Because WIMPs are so elusive, a detector on the surface of the Earth would be overwhelmed by the noise of cosmic rays. Therefore, experiments like LUX ZEPL in South Dakota and Xenon NNT in Italy are located nearly a mile underground, sheltered by thick layers of rock. These detectors consist of giant vats of ultra-pure liquid xenon. The hope is that once in a very long while, perhaps once a year, a dark matter particle drifting through the Earth will happen to strike a xenon nucleus head-on. This rare nuclear recoil would create a tiny flash of light and a puff of electrons that sensitive sensors can detect. Despite years of searching, we have yet to see a definitive signal, but each day of silence allows us to rule out certain types of WIMPs, narrowing the hiding places for the ghost. But what if dark matter isn't heavy at all? What if it is incredibly light, so light that it behaves more like a wave than a particle? This brings us to the second major candidate, the axion. Originally proposed to solve a technical problem in the physics of the strong force, axions are theoretical particles that are trillions of times lighter than an electron. If they exist, the universe would be filled with a sea of axions, a low-frequency field that permeates everything. Because they are so light, we don't look for them by waiting for a collision. We look for them by trying to convert them into something we can see. The ADMX, or Axion Dark Matter experiment, uses a powerful superconducting magnet to create a field that, in theory, can coax an axion into turning into a photon, a particle of light. The experiment is essentially a super-sensitive radio tuned to the frequency of the dark matter field. Scientists slowly scan the dial, looking for a tiny excess of microwave power that would signal the presence of the dark matter field. Finding an axion would be a double victory. It would solve the dark matter mystery and answer a fundamental question about the nature of nuclear physics. Beyond WIMPs and axions, the dark sector might be even more complex than we imagine. Some theorists propose that there is an entire parallel world of particles, self-interacting dark matter. In this scenario, dark matter doesn't interact with us, but it does interact with itself. It might have its own dark photons and its own dark forces. If dark matter particles can bounce off one another, it would change how they settle into the centers of galaxies, potentially solving the core cusp problem we discussed in earlier chapters. This would mean that the 27% of the universe we call dark matter isn't just one boring particle, but a rich ecosystem of different particles and forces, a dark standard model that mirrors our own but remains invisible to our light. There is also the possibility of sterile neutrinos. We already know that neutrinos exist. They are nearly massless particles that stream through us by the trillions. However, the neutrinos we know are too hot or fast to be the main component of dark matter. Sterile neutrinos are a theoretical fourth type of neutrino that is heavier and even more elusive. They wouldn't even feel the weak nuclear force, interacting only with gravity. Some scientists believe they have seen hints of these particles in X-ray observations of galaxy clusters, where a mysterious 3.5 keV line might be the signal of a sterile neutrino slowly decaying into light. While the evidence is still debated, it remains a tantalizing lead in the cosmic cold case. While these experiments look for particles passing through the Earth, other scientists are trying to create dark matter from scratch. At the Large Hadron Collider at LHC at CERN, physicists smash protons together at nearly the speed of light, recreating the high-energy conditions of the Big Bang. They look for events where energy seems to disappear.
Because energy must be conserved, if a collision produces a dark matter particle, that particle will sail out of the detector without leaving a trace, creating an imbalance in the energy budget. This missing energy would be the signature of a dark matter particle being born in the lab. So far, the LHC has not found a clear dark matter signal, but as it moves into higher energies and higher luminosities, the chance of a discovery grows. We also look for indirect detection in the heart of the galaxy. If dark matter particles are their own antiparticles, they might occasionally collide with one another and annihilate, turning into high-energy gamma rays. Telescopes like the Fermi Gamma Ray Telescope have seen a mysterious galactic center excess, a glow of gamma rays from the middle of the Milky Way that is difficult to explain with known pulsars or gas clouds. Many believe this could be the smoke from the dark matter fire, the signal of invisible particles destroying themselves in the densest part of our galaxy's halo. As we conclude this 25,000-word exploration, we must reflect on what it means to live in a dark universe. We are at a unique moment in human history. For the first time, we have mapped the boundaries of our own ignorance. We know exactly how much of the universe is missing, and we have a suite of global experiments closing in on the answer. Identifying the dark matter particle will be a Copernican moment. Just as Copernicus showed us that the Earth is not the center of the solar system, dark matter shows us that atoms are not the center of the universe. We are a small, luminous fraction of a much larger, darker reality. The story of dark matter is the story of the universe's secret life. It is the story of the silent architect that built the house we live in. It is a story that is still being written in the silent halls of underground mines, in the heart of massive supercomputers, and in the lenses of telescopes orbiting the Earth. We are the light that is finally beginning to illuminate the dark. The ghost is real, and we are almost close enough to touch it.
For the entirety of human history, we have been victims of a grand celestial illusion. We looked at the night sky and saw the stars, the planets, and the glowing dust of the Milky Way, and we naturally assumed that this was the universe. We believed that light was the language of reality. If we could see it, it existed. If we couldn't see it, it was simply empty space. But as we sit here in the year 2026, armed with the most powerful instruments ever conceived by the human mind, the James Webb Space Telescope, JWST, the Euclid mission, and the Vera C. Rubin Observatory, we have been forced to swallow a humble, almost terrifying truth. Everything we have ever seen, every star in the billions of galaxies across the observable horizon, is nothing more than the thin, glowing foam on top of a vast, dark, and invisible ocean. When you look at the famous pillars of creation or the deep field images of the early universe, you are looking at less than 5% of what is actually there. The remaining 95% of the universe is composed of things we cannot see, cannot touch, and, until very recently, could barely even conceive. This is the dark sector. It is divided into two mysterious titans, dark energy, which pushes the universe apart, and our focus today, dark matter, the invisible architect that holds everything together. The architecture of ghosts. Why do we call it architecture? In a city like New York or Tokyo, the architecture is the steel, the concrete, and the rebar. You see the glass windows and the bright neon signs, but without the hidden steel skeleton, the skyscraper would collapse under its own weight. The universe operates on the exact same principle. The stars, the planets, and the gas clouds, the normal matter, are the neon signs. They are beautiful, they are bright, and they catch our attention, but they have almost no structural integrity on their own. Dark matter is the rebar. It is the invisible skeleton upon which the visible universe is draped. It is a substance that possesses mass and gravity, but it refuses to play by the rules of light. It does not emit radiation. It does not reflect a single photon. It does not absorb the glow of nearby suns. If you were to walk into a room filled with dark matter, you wouldn't see it, you wouldn't smell it, you wouldn't even feel it brushing against your skin. You would pass through it, and it would pass through you, as if both of you were ghosts. And yet, this ghost is 5 times more prevalent than the atoms that make up your DNA, your home, and your planet. Every second, billions of dark matter particles are likely streaming through your body at incredible speeds, yet they leave no trace. They are the silent majority of the cosmos. The gravitational anchor. How do we know it's there if we can't see it? The answer lies in the only language dark matter speaks: gravity. Gravity is the great snitch of the universe. It tells us exactly where mass is located, even if that mass is hiding in the shadows. In the 1930s, an eccentric but brilliant astronomer named Fritz Zwicky looked at the Coma Cluster, a massive group of thousands of galaxies, and noticed something impossible. The galaxies were zipping around so fast that they should have flown off in all directions, like unrestrained children on a hyperspeed merry-go-round. There wasn't enough visible mass to hold them together. Zwicky called this missing influence dunkle materia, dark matter. Decades later, Vera Rubin confirmed this on a smaller scale by observing individual galaxies. She found that the outer edges of galaxies were spinning just as fast as the centers. According to Newton's rules, this shouldn't happen. The further you are from the center of gravity, the slower you should orbit. But galaxies weren't following Newton's rules. They were behaving as if they were encased in a massive, heavy, invisible ball of matter that provided extra gravitational grip. This was the birth of the unseen architecture theory. We realized that galaxies aren't just collections of stars, they are islands of light floating in vast lakes of dark matter. This invisible substance acts as a gravitational anchor. It prevents the Milky Way from disintegrating. It keeps our sun in its orbital path. Without the extra pull of dark matter, the stars in our night sky would have drifted away into the intergalactic void billions of years ago. We would be alone in a dark, empty expanse without a galaxy to call home. The cosmic scaffolding. But the architecture goes deeper than just holding individual galaxies together. To understand the true scale of dark matter, we have to go back to the beginning of time, the Big Bang. In the immediate aftermath of the Big Bang, the universe was a hot, dense, and perfectly smooth soup of particles. As it expanded and cooled, tiny ripples began to form. These ripples were the blueprints for the universe we see today. However, ordinary matter, the stuff we are made of, was too slippery to clump together. It was under too much pressure from light and radiation. It was like trying to build a sandcastle while a leaf blower is pointing at the sand. Dark matter, however, was immune to that pressure because it doesn't interact with light. It could begin clumping together immediately. It formed the first puddles of gravity. Those puddles grew into wells, and eventually those wells grew into the vast filaments of the cosmic web. Only after the dark matter had built this invisible scaffolding could the ordinary gas and dust fall into these gravitational traps. Once the gas fell in, it became dense enough to ignite. The first stars were born inside nests of dark matter. The first galaxies were constructed on the foundations of dark matter. This means that every structure you see in a NASA photograph, from the sprawling spiral of the Whirlpool galaxy to the dense clusters of the Hubble Deep Field, is there because dark matter built the house first. We are merely the tenants. We are the visible decorations living inside a dark, ancient architecture that was established seconds after the dawn of time. The ultimate challenge to physics. As we stand in the modern era of quantum physics and general relativity, dark matter remains the greatest X factor in our equations. It is the wall we keep hitting. Some skeptics argue that dark matter isn't a substance at all, but rather a sign that our understanding of gravity is wrong. They propose theories like MOND, modified Newtonian dynamics, suggesting that gravity simply behaves differently over large distances. However, every time we test this, the evidence for dark matter becomes stronger.
Whether it's the way light bends around invisible mass, gravitational lensing, or the way the cosmic microwave background is patterned, all roads lead back to a physical, invisible substance. The search for this substance is the most expensive and complex Easter egg in human history. We have built detectors kilometers underground to shield them from noise, hoping to catch a single dark matter particle bumping into a xenon atom. We have sent billion-dollar telescopes into the L2 orbit to map the shadows of this material across the sky. Why? Because until we identify what dark matter is, we don't truly understand the universe. We are like people trying to understand a car by looking only at the paint job, without ever opening the hood to see the engine. Dark matter is the engine. It is the reason there is something rather than nothing. It is the reason the universe isn't just a boring, uniform fog of cooling gas. The scale of our ignorance. To wrap our heads around Chapter 1, we must accept the scale of our own ignorance. Imagine the entire history of human knowledge as a book. We have spent thousands of years writing the first chapter, the chapter on atoms. We've mastered chemistry, built nuclear reactors, and sequenced the human genome. We feel very smart. But dark matter represents the next 95 chapters of that book. It is a form of matter that doesn't follow the standard model of particle physics. It doesn't have a place on the periodic table. It is extraordinary. As we move forward into the next sections of this documentary, we will look at the specific crimes dark matter has committed, the evidence it has left behind in the rotation of galaxies, the bending of starlight, and the echoes of the Big Bang. We will see how it has shaped our own Milky Way, and how it is currently streaming through your room, through your screen, and through your body, silent and heavy, the invisible master of the cosmos. This is not just a story about space, it is a story about the 95% of reality we are just beginning to see. Welcome to the unseen architecture.
The perfect harmony of the solar system. To understand why galaxies are broken, we first have to look at something that works perfectly, our own solar system. Since the days of Johannes Kepler and Isaac Newton, we have possessed a cosmic ruler for gravity. This ruler tells us a simple, unwavering truth. The further away an object is from a source of gravity, the slower it must travel to stay in orbit. Think of Mercury. It is the sprinter of our system, screaming around the sun at nearly 170,000 kilometers per hour. Why? Because the sun's gravitational pull at that proximity is a violent, dragging force. If Mercury slowed down even slightly, it would be swallowed by the solar furnace. Now look at Neptune, billions of miles away. The sun's grip there is faint, a mere ghostly tug. Consequently, Neptune moseys along at a leisurely 19,000 kilometers per hour. This is a Keplerian decline. It's a mathematical curve that drops off beautifully as distance increases. It is the law of the land. It's how we launch satellites, how we landed on the moon, and how we navigate probes to the outer reaches of the heliosphere. We assumed, with the typical arrogance of our species, that this law was universal. We assumed that a galaxy, which is essentially just a much larger version of a solar system, would follow the same curve. We were wrong. The discovery that changed everything. Enter Vera Rubin. In the late 1960s and early 70s, Rubin, along with her colleague Kent Ford, turned her attention to the Andromeda Galaxy, M31, our nearest giant neighbor. At the time, the scientific consensus was settled. The bright, bulging center of Andromeda contained the vast majority of its mass. Therefore, the stars on the distant, dim edges of the galaxy should be moving slowly, just like Neptune. Rubin used a state-of-the-art spectrograph to measure the Doppler shift of the light coming from those outer stars. By looking at how the light stretched or compressed, she could calculate exactly how fast those stars were traveling. She expected to see a curve that started high near the center and plummeted toward the edges. Instead, she saw a flat line. The stars at the very edge of Andromeda, 70,000 light-years from the center, were moving at the exact same velocity as the stars much closer in. It was as if Neptune decided to race Mercury and actually kept pace. This wasn't just a weird observation, it was a physical impossibility.
According to the visible mass of the galaxy, the sum total of every star, gas cloud, and black hole we could see, there simply wasn't enough gravity to hold on to those stars at those speeds. The merry-go-round analogy. Let's put this in human terms. Imagine you're at a local park, standing next to a merry-go-round. You start spinning it by hand. If a child is sitting right next to the center pole, they feel a slight tug. If a child is hanging on to the very outer railing, they feel a much stronger force trying to fling them off. Now imagine you attach a jet engine to that merry-go-round and spin it at 500 miles per hour. What happens? The railing breaks, the bolts shear off, the children are launched into the next county. Centrifugal force wins. A galaxy is that merry-go-round. The stars at the edge are traveling at roughly 200 to 250 kilometers per second. Based on the amount of stuff we can see, the galaxy's bolts should have sheared off billions of years ago. Andromeda should have disintegrated. The Milky Way should have sprayed its stars across the void like a lawn sprinkler. The fact that galaxies exist at all, that they hold their beautiful coiling shapes, is proof that there is a hidden hand holding the railing in place. The mass gap. This is where the math gets haunting. When Rubin and other astronomers calculated how much extra gravity was needed to keep these galaxies together, the numbers didn't just tweak our understanding, they demolished it. To keep those outer stars in orbit, a galaxy needs about 5 to 6 times more mass than what is visible. Imagine walking into a grocery store and picking up a bag of apples. The bag says 1 pound. You put it on the scale, and the scale reads 6 pounds. You look inside, you count the apples, there are only 3 apples. There is no lead weight at the bottom, there is no heavy packaging, the bag is physically light to the touch, yet the scale insists it is heavy. That is the galaxy rotation puzzle. It suggested that for every star we see, there are 5 stars worth of something else that we cannot see. This something doesn't just sit in the center, it is spread out in a massive, invisible dark matter halo that encapsulates the entire galaxy. This halo provides a constant, steady gravitational floor that keeps the rotation curve flat. Newton versus Einstein versus the unknown. When Rubin's data was published, the scientific community went into a defensive crouch. Physicists are loath to invent new forms of matter if they don't have to. The first instinct was to fix the math. This led to the rise of MOND, modified Newtonian dynamics. The proponents of MOND argued that perhaps Newton's laws simply change when gravity becomes extremely weak, such as at the edges of a galaxy. They suggested that maybe F equals ma needs a small correction factor at low accelerations. It was a brilliant attempt to save the standard model of physics without resorting to ghost matter. But as the years went on, MOND began to fail. It could explain some galaxy rotations, but it couldn't explain how galaxy clusters stayed together. It couldn't explain how light bent around empty space. Dark matter, however, explained everything. If you simply accepted that there was a physical particle that had mass but didn't interact with light, the universe suddenly made sense again. The rotation puzzle wasn't a failure of our equations, it was a success of our observation. We had discovered a new ingredient in the cosmic recipe. Vera Rubin's legacy. It is important to pause and acknowledge the human side of this puzzle. Vera Rubin faced immense hurdles as a female astronomer in the mid-1960s. She was told she couldn't use certain telescopes. She was told her data was likely an instrumental error. But she was meticulous. She mapped dozens, then hundreds of galaxies. Every single one of them told the same story. The stars are moving too fast. Her work shifted the paradigm of cosmology. We went from living in a universe of light to living in a universe of shadows. We realized that the normal matter we are made of is actually the anomaly. We are the 5%. We are the impurities in a vast sea of dark matter. Today, the Vera C. Rubin Observatory in Chile, one of the most advanced survey telescopes ever built, is nearing completion. Its primary mission? To map the very dark matter she discovered. It will take time-lapse movies of the sky, watching how the unseen architecture pulls on the visible world.
The rotation puzzle remains the most tactile evidence we have. It's the closest we've come to touching dark matter. We can see its muscles rippling under the skin of the galaxy. We know how much it weighs, we know where it sits, and we know that without it, our sun would be a lonely wanderer in a dark, structureless abyss. The mystery deepens. But if every galaxy is sitting inside a giant invisible ball of mass, what does that mean for our neighborhood? If the Milky Way is spinning too fast, what is happening right here in our own solar system? Is dark matter flowing through your living room right now? In the next chapter, we're going to shrink our focus from the distant edges of Andromeda to our own backyard. We're going to explore the Milky Way's invisible halo and the terrifying reality that we are currently submerged in a dark, high-speed wind of particles that are millions of times more numerous than the atoms in your body. The rotation puzzle was just the beginning. Now the mystery hits home.
The Milky Way galaxy, our celestial home, is often visualized as a flat, shimmering disk of stars and gas spiraling around a central core. However, modern astrophysics has revealed that this visible structure is merely a small island inhabiting a much larger, invisible ocean. To understand the true scale of our galaxy, we must look beyond the starlight and recognize the existence of the Milky Way's dark matter halo. This is not a secondary feature, it is the primary gravitational structure of our system. While the visible disk of the Milky Way spans approximately 100,000 light-years, the dark matter halo is estimated to reach nearly 1 million light-years into the intergalactic void. This means that for every kilometer of space occupied by stars and glowing nebulae, there are 10 kilometers of space dominated entirely by invisible mass. This halo is a massive, roughly spherical cocoon that provides the gravitational well in which our galaxy sits. Without this protective envelope of dark matter, the Milky Way would lack the structural integrity to hold on to its outer stars, and the beautiful spiral arms we see in telescopic images would have disintegrated billions of years ago. The evidence for this local halo comes from the study of galactic dynamics. When astronomers measure the speeds of globular clusters in satellite galaxies, the smaller galactic neighbors that orbit the Milky Way, they find that these objects move as if they are being pulled by an immense hidden weight. If the Milky Way consisted only of the stars and gas we can see, these distant satellites would be traveling far above the escape velocity of the galaxy and would have flown off into deep space. The fact that they remain in stable, long-term orbits is the definitive proof that the Milky Way is far heavier than it appears. Recent data from the Gaia space mission has allowed scientists to weigh the Milky Way with unprecedented precision by tracking the 3D motions of over 1 billion stars. The results are staggering. The total mass of the Milky Way is approximately 1.5 trillion times the mass of our Sun. Since the visible matter accounts for only a small fraction of this total, we are forced to conclude that roughly 85 to 90% of our galaxy's mass is composed of dark matter. We are living inside a massive gravitational basin, the bottom of which is lined with a substance we cannot see, touch, or detect with conventional telescopes. This realization brings the mystery of dark matter directly into our local environment. Because the Sun is orbiting the center of the galaxy at a speed of approximately 230 kilometers per second, we are effectively plowing through this dark matter halo as we move. If dark matter is made of particles, as the leading cold dark matter theories suggest, then there is a constant dark matter wind blowing through the Earth at all times. This is not a metaphor, it is a physical reality. As you read these words, billions of dark matter particles are streaming through your body every single second. They pass through the atoms of your cells, the walls of your home, and the very core of the Earth without ever slowing down or leaving a trace. Because dark matter does not interact with the electromagnetic force, it is an important clue. Because dark matter does not interact with the electromagnetic force, it does not bump into normal matter. To a dark matter particle, a solid lead wall is as transparent as a photon is to a window. We are submerged in a high-density sea of the universe's most mysterious ingredient, yet our biological senses and our most sensitive electronic instruments are almost entirely blind to it. The structure of the Milky Way's halo is also a record of our galaxy's violent past. Astronomers have discovered stellar streams, long, thin ribbons of stars that wrap around the galaxy like cosmic threads. These streams are the remains of smaller dwarf galaxies that were captured by the Milky Way's gravity and torn apart by tidal forces. These streams act as sensitive detectors for the dark matter halo. If the halo were perfectly smooth, these star streams would be uniform and narrow. However, observations show that these streams often have gaps or kinks in them. These disturbances are believed to be the wakes left behind by dense clumps of dark matter called subhalos that have passed through the streams. These subhalos are entirely invisible. They contain no stars and no gas, yet their gravity is strong enough to scatter a line of stars. By mapping these disruptions, scientists are creating a topographic map of the invisible. This confirms that our halo is not a static, boring cloud, but a turbulent and lumpy environment filled with dark, massive objects that roam our galaxy like silent predators. Furthermore, the dark matter halo plays a decisive role in the long-term evolution of the local group. The Milky Way and the Andromeda Galaxy are currently falling toward each other at about 110 kilometers per second. While the visible edges of the two galaxies are still millions of light-years apart, their dark matter halos are so large that they are likely already beginning to overlap. This means the merger has already started in the invisible realm. As these two massive halos interact, they create dynamical friction, which acts like a cosmic brake, slowing the galaxies down and ensuring they eventually spiral into one another to form a single, massive elliptical galaxy. The invisible architecture is the collision zone, where the fate of our galaxy is being decided. The stars are simply along for the ride, tracers of a much larger and more powerful gravitational dance. The density of dark matter in our local neighborhood is a subject of intense research. While it dominates the galaxy on a large scale, its density within our solar system is relatively low. Within the volume of the Earth, there was only about 1 gram of dark matter at any given time, roughly the mass of a paperclip. This explains why dark matter doesn't interfere with the orbits of the planets or the falling of an apple from a tree. On these small scales, the concentrated mass of the Sun and the Earth far outweighs the diffuse background of dark matter. However, across the thousands of light-years that define the galaxy, this diffuse mass adds up to a staggering total. It is the macro-architecture that allows the micro-architecture of stars and planets to exist. Without the halo's gravity, the gas in the early galaxy would never have been compressed enough to form the Sun, and the stars would never have been held together in a stable disk. We owe our existence to this invisible cocoon. Understanding the Milky Way's halo also allows us to test the fundamental nature of dark matter itself. If dark matter were warm, meaning the particles moved very fast in the early universe, it would be difficult for it to gather into the small, dense clumps or subhalos that cause the gaps in stellar streams. If it is cold, as the evidence currently suggests, we expect to see a halo filled with thousands of these dark substructures. The search for these dark satellites is one of the important frontiers in modern astronomy. By using the motions of stars as our guide, we are effectively using the galaxy as a laboratory to study the properties of a particle that no Earth-based collider has yet been able to produce. We are reading the gravitational braille of the night sky to feel the shape of the dark matter that surrounds us. In conclusion, the Milky Way's dark matter halo is the silent master of our galactic neighborhood. It is a massive, heavy, and ancient structure that dictates the movement of stars, the survival of satellite galaxies, and the ultimate destiny of our system. It is a reminder that the universe is not what it seems. We are the 5% minority, the visible dust on a much larger and darker machine.
As we look out at the stars, we must remember that we are looking through a thick, invisible fog of mass that has been there since the dawn of time, providing the foundation for everything we know. In the next stage of our investigation, we will look back at the very beginning of the universe to see how this architecture was first constructed.
The story of our origins begins roughly 13.8 billion years ago with the Big Bang, but the universe we see today, filled with grand spiral galaxies, dense star clusters, and complex heavy elements, was by no means a guaranteed outcome. In the immediate aftermath of the cosmic dawn, the universe was a nearly perfectly smooth, searingly hot soup of radiation and elementary particles. For the first few 100,000 years, the cosmos was opaque, a roiling plasma where light and matter were inextricably locked together. If the universe had been composed only of the normal baryonic matter we are made of, the timeline of cosmic evolution would have been radically different, and it is highly probable that life-bearing galaxies like the Milky Way would never have had the time to form before the expansion of space pushed matter too far apart to ever coalesce. This chapter explores why dark matter was the essential engine of structural growth and how it provided the gravitational head start necessary for the first stars to ignite. In the infant universe, normal matter faced a fundamental physical hurdle known as radiation pressure. Because protons and electrons are electrically charged, they interacted constantly with the intense bath of photons filling the young cosmos. Every time a clump of normal gas tried to pull itself together under its own gravity, the internal pressure of the radiation pushed right back, smoothing the clump out like a wave being flattened on a beach. This created a state of pressure-supported equilibrium. Normal matter was essentially slippery. It could not settle down into dense pockets because it was being constantly buffeted by the white-hot light of the early universe. Had this been the only form of matter, the process of forming the first stars would have been delayed by billions of years, waiting for the universe to expand and cool to a point where gravity could finally overcome this electromagnetic pushback. Dark matter, however, operated under a completely different set of rules. Because dark matter does not interact with light, it has no electric charge and does not feel the electromagnetic force, it was immune to radiation pressure. While the normal matter was being pushed around by photons, the dark matter was already hard at work building the foundations of the universe. From the very first fractions of a second after the Big Bang, tiny quantum fluctuations in the density of dark matter began to grow. Because it only felt gravity, dark matter began to collapse into the first gravitational wells almost immediately. It didn't have to wait for the universe to cool or for the radiation to subside. It started clumping together while the cosmos was still a fraction of its current size. These dark matter concentrations acted as the universe's first gravity traps, creating deep pits in the fabric of spacetime. By the time the universe reached an age of about 380,000 years, a milestone known as recombination, the temperature finally dropped enough for electrons and protons to form neutral hydrogen atoms. At this exact moment, the radiation was released, becoming the cosmic microwave background that we still detect today. Suddenly, normal matter was no longer being pushed by light. It was finally free to respond to gravity. But it didn't have to start from scratch. When the gas finally looked around, it found a universe already populated by massive, pre-existing structures of dark matter. The normal gas simply slid into the deep gravitational pockets that the dark matter had already prepared. This is why we see mature galaxies appearing in the deep field images of the James Webb Telescope at a time when the universe was only a few 100 million years old. Dark matter had provided a multi-million-year head start, acting as the nests in which the first stars could safely hatch. This process is what astrophysicists call hierarchical structure formation. The dark matter didn't just form one giant clump, it formed millions of tiny halos. Inside these small halos, the normal hydrogen gas became compressed and hot. As the gas collided with itself, it lost energy through radiation and sank deeper into the center of the dark matter well. Eventually, the density became so high and the temperature so extreme that nuclear fusion ignited. These were the first stars, massive, short-lived giants that began the process of lighting up the dark scaffolding.
Without the concentrated gravity of a dark matter halo to pull the gas in, the gas would have remained too diffuse to ever reach the pressures required for fusion. Dark matter was the midwife of the first starlight. As these first star-forming regions grew, they began to merge. Because dark matter makes up about 85% of the total matter in the universe, the gravitational pull between these early halos was immense. They crashed into one another, building larger and larger structures in a cosmic game of winner takes all. This is how the first proto-galaxies were assembled. We can think of dark matter as the hidden skeleton, and normal matter as the flesh that eventually grows over it. If you look at a modern simulation of the early universe, such as the Millennium simulation or Illustris, you see a terrifyingly beautiful web of dark matter filaments. The normal gas flows along these filaments like water through a pipe, gathering at the intersections to form the massive galaxies we see today. The speed at which this happened is one of the strongest proofs for the existence of dark matter. A universe made only of atoms simply could not have built something as complex as a galaxy in the time available since the Big Bang. The timing of this gas inflow also determined the chemistry of our universe. The first stars, born in these dark matter nests, were composed entirely of hydrogen and helium. When they exploded as supernovae, they forged the heavier elements, carbon, oxygen, iron, and gold, and spewed them back into the dark matter wells. Because the dark matter halos were so massive, they acted like gravitational buckets, catching this enriched gas and preventing it from flying off into the void. This allowed the next generation of stars to be born with the chemical ingredients necessary for planets and eventually life. We are literally made of stardust that was caught and recycled by the invisible hands of dark matter. If the halos hadn't been there, the heavy elements would have been lost to the vastness of space, and the second generation of stars, including our own sun, would have been chemically poor, incapable of supporting rocky planets or biological life. Furthermore, the cold nature of dark matter was crucial during this epoch. If dark matter were hot, meaning its particles were moving near the speed of light, it would have moved too fast to be caught in small gravitational wells. It would have streamed away, smoothing out any small-scale ripples. In a hot dark matter universe, the first structures to form would have been massive, supercluster-sized sheets of matter, which would only later fragment into galaxies. However, when we look back with our most powerful telescopes, we see the opposite. We see small, chaotic galaxies forming early and merging into larger ones. This bottom-up growth is a definitive print of cold dark matter. It tells us that the particles making up the invisible architecture must be relatively heavy and slow-moving, allowing them to clump on small scales and build the universe piece by piece. As we conclude this chapter on the early universe, we must recognize that dark matter is not just a filler for the empty parts of space, it is the fundamental reason the universe has any structure at all. It is the reason the normal matter was able to overcome the chaotic energy of the Big Bang and organize itself into coherent systems we call galaxies. We live in a universe of islands because the dark matter built the archipelagos long before the first light ever shone. The rapid formation of galaxies is the ultimate testament to this unseen influence. In the next chapter, we will move forward in time to see how this early clumping evolved into the largest structure in existence, the cosmic web.
If we were to pull back from our local neighborhood and zoom out until even the massive clusters of galaxies looked like tiny grains of sand, we would witness the true face of the universe. It is not a random scattering of points, nor is it a uniform fog. Instead, the universe is organized into a vast, intricate network known as the cosmic web. This structure is the largest coherent entity in existence, spanning billions of light years. It consists of enormous, thin filaments of matter, dense intersections called nodes, in gargantuan, empty regions known as cosmic voids. While we see this web through the light of the galaxies that inhabit it, the silk of this web is not made of stars. The entire structure is a gargantuan skeleton of dark matter. In this chapter, we explore how dark matter acted as the primary architect for this cosmic geography, and why the large-scale structure of the universe is the ultimate proof of an invisible hand at work. The concept of the cosmic web began as a theoretical prediction from supercomputer simulations, such as the Millennium and Illustris projects.
When cosmologists programmed the laws of gravity into these machines and allowed a simulated universe to evolve from the Big Bang, they found that a universe containing only normal matter remained stubbornly smooth. Without an additional source of gravity, the expansion of the universe was too rapid for galaxies to group together into long, thin strands. However, when the dark matter ingredient was added, specifically cold dark matter, the simulations suddenly transformed. The dark matter began to collapse into a complex network of sheets and filaments. The normal gas, drawn by the immense gravity of these dark structures, flowed into the filaments like water into a drainage pipe, eventually collecting at the crossroads where multiple filaments met. These crossroads became the birthplaces of massive galaxy clusters, containing thousands of individual galaxies. This dark matter scaffolding is what defines the geography of the universe. Think of it like the interstate highway system of a continent. The cities, galaxy clusters, only exist because the highways, dark matter filaments, provided the route for resources and matter to travel. Between these highways lie the voids, vast spherical bubbles of space that are almost entirely empty of both galaxies and dark matter. These voids can be hundreds of millions of light-years across. They exist because over billions of years, the dark matter filaments have acted like gravitational vacuum cleaners, sucking all the nearby gas and dust out of the voids and into the dense strands of the web. This process has created a Swiss cheese-like structure where most of the universe's volume is empty, but most of its mass is concentrated into a thin, interconnected network. How do we know this web is real and not just a computer-generated fantasy? The proof comes from massive sky surveys, such as the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey. By measuring the three-dimensional positions of millions of galaxies, astronomers have mapped the large-scale structure of the sky. The results perfectly match the simulations. We see the Great Wall, the Hercules Corona Borealis Great Wall, and other massive filaments of galaxies stretching across the horizon. But here is the critical part. The amount of visible matter in these galaxies is nowhere near enough to hold these filaments together. If there were no dark matter, these great walls would lack the gravitational strength to exist. They would have dissolved as the universe expanded. The very fact that we see a web at all is evidence that an invisible, heavy framework is providing the tension to keep the filaments intact. One of the most profound ways we study this scaffolding is through weak gravitational lensing. Because the cosmic web is so massive, its gravity slightly warps the space around it. When the light from extremely distant galaxies passes through a dark matter filament on its way to Earth, the light is subtly distorted. By analyzing the shapes of millions of background galaxies, astronomers can reconstruct the mass that caused the distortion. This has allowed us to create dark matter maps that show the filaments even in places where there are no shining galaxies. These maps confirm that the dark matter is exactly where the simulations predicted it should be, forming long, invisible bridges between the clusters of galaxies. The silk of the web is real, it has weight, and it is the true master of cosmic motion. The cosmic web also serves as a time capsule of the early universe. The thickness of the filaments and the size of the voids are directly related to the conditions that existed just fractions of a second after the Big Bang. Specifically, they're influenced by baryon acoustic oscillations, sound waves that traveled through the primordial plasma. Dark matter preserved the crests of these sound waves through its gravity, locking them into the large-scale structure we see today. By measuring the distance between the nodes of the cosmic web, scientists can calculate the expansion rate of the universe with incredible precision. This makes the dark matter web not just a structure, but a standard ruler that allows us to measure the history and fate of the entire cosmos. Furthermore, the environment of the cosmic web dictates the life and death of galaxies. Galaxies located in the dense nodes or clusters tend to be older, redder, and dead, meaning they have stopped forming stars. This is because the extreme gravity and high-speed collisions in these dark matter hubs strip the galaxies of their life-giving gas. In contrast, galaxies found along the filaments are often still healthy and blue, slowly feeding on the gas that flows toward them along the dark matter pipes.
In the web is a living, breathing ecosystem where the invisible dark matter infrastructure determines which galaxies will thrive and which will wither away. As we look at the cosmic web, we are forced to confront a shift in perspective. We usually think of a galaxy as an individual entity, but in the context of the large-scale structure, a galaxy is just a single pixel in a much larger image. The canvas is the dark matter. Without the canvas, the pixels would have no place to sit. The universe is not a collection of objects. It is a single, interconnected field of dark matter that has spent 13.8 billion years organizing itself into this magnificent web-like architecture. In conclusion, the cosmic web is the ultimate manifestation of dark matter's power. It is a structure so large it defies human comprehension, yet it is held together by a substance so elusive we can't even see it. It proves that the invisible is the dominant force in the universe, shaping the very geography of existence. In the next chapter, we will go back to the origins of this discovery and look at the missing mass problems in galaxy clusters that first hinted at this gargantuan hidden reality.
To understand why we are so certain of dark matter's existence, we must look at the largest laboratories in the universe, galaxy clusters. These are the most massive gravitationally bound structures in the cosmos, containing anywhere from hundreds to thousands of individual galaxies, all swarming around a common center of mass. In the 1930s, long before we had space telescopes or supercomputers, the first cracks in our understanding of visible physics appeared within these gargantuan systems. It was here that the missing mass problem was first identified, suggesting that the universe was hiding something far heavier than the stars themselves. This chapter explores the historical and physical evidence found within these clusters and why they remain the most uncompromising witnesses to the dark matter mystery. The story begins with the eccentric and brilliant Swiss-American astronomer Fritz Zwicky. In 1933, Zwicky was observing the Coma Cluster, a dense collection of over 1,000 galaxies located about 320 million light-years away. Zwicky was interested in the dynamics of the cluster, essentially how fast the individual galaxies were moving. Using the Doppler effect to measure their velocities, he expected to find a relatively sedate pace. According to the laws of gravity established by Newton and Einstein, the speed of an object in orbit is determined by the total mass of the system. If the Coma Cluster only contained the stars that were visible through a telescope, the gravity should have been relatively weak and the galaxies should have been moving at modest speeds. However, Zwicky's measurements revealed a chaotic, high-speed swarm. The galaxies were zipping around at speeds of thousands of kilometers per second, far faster than the visible matter could possibly account for. Zwicky performed a virial theorem calculation, a mathematical way of balancing the kinetic energy of motion against the potential energy of gravity. He reached a startling conclusion. To keep these galaxies from flying away and dissolving the cluster, there had to be at least 400 times more mass than what was visible in the form of stars. He famously coined the term Dunkel Materie, or dark matter, to describe this invisible weight that was providing the necessary gravitational grip. At the time, his peers largely dismissed the finding as a measurement error or a temporary anomaly, but Zwicky had stumbled upon the first evidence of the universe's silent majority. The missing mass problem in clusters isn't just about the speed of galaxies, it's also about the hot gas that fills the space between them. When we look at galaxy clusters using X-ray telescopes like NASA's Chandra Observatory, we see something the 1930s astronomers couldn't: the intra-cluster medium. This is a vast atmosphere of superheated plasma that glows brilliantly in the X-ray spectrum. This gas is incredibly hot, reaching temperatures of tens of millions of degrees. At such extreme temperatures, the particles are moving so fast that they want to expand and drift away into the intergalactic void. The only thing capable of holding this gas inside the cluster is gravity. When astrophysicists calculate the amount of gravity required to confine this high-pressure gas, the numbers once again refuse to cooperate. Even when you add up all the mass of all the stars in the galaxies and the mass of the hot gas itself, which actually outweighs the stars, you still fall far short of the total mass needed to prevent the gas from escaping.
There is a massive shortfall in the gravitational budget. Without an additional, invisible source of mass, these clusters would be empty. The gas would have evaporated billions of years ago. The persistent presence of this hot, trapped plasma is a 24-hour-a-day proof that dark matter is wrapping these clusters in a deep, invisible gravitational blanket. Furthermore, galaxy clusters allow us to weigh the universe through a phenomenon called strong gravitational lensing. Because a cluster is so massive, it acts like a giant magnifying glass in space. It warps the fabric of space-time so severely that the light from even more distant galaxies, located far behind the cluster, is bent and distorted as it passes through. This effect is purely geometric. It depends only on the total amount of mass in the cluster, regardless of whether that mass is bright or dark. By analyzing these distorted images, astronomers can create a gravity map of the cluster. This is perhaps the most convincing evidence of all. When we compare these gravity maps to the maps of where the stars and gas are located, we find a perfect, yet haunting alignment. The gravity peaks are exactly where they should be to hold the cluster together, but they are often located in empty spaces where there are very few stars. We are literally seeing the shadow of the dark matter. We can see exactly where it is concentrated, how it is distributed, and how it is holding the entire cluster in a firm gravitational embrace. This lensing mass is consistently 5 to 10 times greater than the visible mass. The clusters are not just collections of galaxies, they are massive piles of dark matter that happen to have a few shining galaxies trapped inside them. The stability of these clusters over billions of years also points to the nature of dark matter. If dark matter were hot, moving at relativistic speeds, it wouldn't stay clumped inside the cluster. It would zoom out and become a smooth, universal fog. The fact that the mass remains concentrated within the cluster boundaries tells us that dark matter is cold. It moves slowly enough to be captured by the cluster's gravity and stay there for the age of the universe. This provides the anchor that allows clusters to grow and merge over time, eventually becoming the massive nodes of the cosmic web we discussed in the previous chapter. As we look at the Coma cluster or the Perseus cluster today, we are seeing a cosmic bookkeeping error that hasn't gone away nearly a century. Every technique we use to weigh these giants, whether it's the speed of the galaxies, the temperature of the X-ray gas, or the bending of starlight, yields the same answer. There is a vast, hidden component that dominates the gravity of the cluster. It is the missing mass that makes the universe work. Without it, the largest structures in the cosmos would simply fall apart. In conclusion, galaxy clusters are the definitive weight stations of the universe. They prove that the dark matter mystery is not just a quirk of individual galaxies, but a fundamental property of the universe on its largest scales. The missing mass identified by Zwicky has grown from a fringe theory into the cornerstone of modern cosmology. In the next chapter, we will look at how this evidence was refined by the work of Fritz Zwicky himself and the later undeniable observations of Vera Rubin.
The history of dark matter is often told as a modern detective story, but its roots stretch back to a time before the discovery of the double helix or the invention of the digital computer. To truly grasp the magnitude of the dark matter mystery, we must travel back to the early 1930s and meet one of the most brilliant, abrasive, and prophetic figures in the history of science, Fritz Zwicky. A Swiss-born astronomer working at the California Institute of Technology, Caltech, Zwicky possessed a mind that thrived on morphological thinking, a method of looking at every possible permutation of a physical problem. While his peers were busy cataloging the light of the stars, Zwicky became obsessed with the things that were not shining. He was the first to realize that the universe we see is merely a fraction of the universe that exists, and he did so by treating a cluster of galaxies like a simple physical swarm. In 1933, Zwicky turned the 18-inch Schmidt telescope at Palomar Observatory toward the Coma cluster, a dense beehive of galaxies located hundreds of millions of light-years away. At the time, astronomers were only just beginning to accept that galaxies were island universes outside our own Milky Way. Zwicky, however, wanted to go deeper. He wanted to understand the totalitarian principle of the cluster, the relationship between the motion of the individual galaxies and the total mass holding them together. He used a spectrograph to measure the redshift and blueshift of the galaxies within the Coma cluster. This allowed him to calculate their peculiar velocities, the speeds at which they were moving relative to the cluster's center. What Zwicky found was a statistical impossibility. The galaxies were moving at a velocity of approximately 1,000 kilometers per second. To a physicist, speed is a direct indicator of energy. According to the virial theorem, a mathematical principle that relates the average kinetic energy of a system to its total gravitational potential energy, this high speed meant the cluster had to have an immense gravitational pull to keep the galaxies from escaping. Zwicky calculated the amount of mass needed to generate that gravity. Then he calculated the amount of mass actually present in the form of visible stars based on the brightness of the galaxies. The numbers were catastrophic for the physics of the time. Zwicky found that the cluster needed at least 400 times more mass than what was visible to remain stable. If the Coma cluster only contained the stars he could see, it should have flown apart millions of years ago, its member galaxies drifting off into the lonely void of intergalactic space. The fact that the cluster was a tight, bound unit was proof that something massive was hiding in plain sight. In his landmark paper published in the journal Helvetica Physica Acta, Zwicky coined the term Dunkel Materia, dark matter. He argued that the universe was filled with a cold form of matter that possessed weight but refused to emit or absorb light. He was essentially telling the world that the cosmic ledger was out of balance by a factor of hundreds. Zwicky's discovery was met with a resounding silence. Partly this was due to the technical limitations of the era. Measuring the mass of galaxies was an imprecise science, and many of his colleagues believed he had simply made a bookkeeping error or overestimated the distances involved. But the silence was also due to Zwicky's personality. He was a famously difficult man who referred to his fellow astronomers as spherical bastards, meaning they were bastards no matter which way you looked at them. His radical ideas, which included the existence of neutron stars and gravitational lensing decades before they were confirmed, were often dismissed as the wild guesses of a provocateur. Consequently, the missing mass problem sat in the dusty archives of astronomy for nearly 40 years, a dormant volcano waiting for the right evidence to erupt. However, Zwicky's logic was ironclad. He had realized that gravity leaves footprints. Even if a substance is invisible, it cannot hide its pull. He treated the Coma cluster not as a collection of beautiful light-filled objects, but as a swarm of bees in a gravitational cage. If the bees are moving at 100 miles an hour, the cage must be made of steel. If you look and see only a cage made of spider webs, you must conclude that there are invisible steel bars reinforcing the structure. Zwicky was the first person in human history to see those invisible bars. He understood that the luminous stars were just the tracer particles moving through a much deeper and darker sea of mass. It is staggering to consider how far ahead of his time Zwicky was. He didn't just propose that matter was missing, he proposed that it was dark. He correctly intuited that this matter wasn't just dim stars or gas, but something fundamentally different that didn't interact with the electromagnetic spectrum. He also predicted that these massive dark matter concentrations would act as gravitational lenses, bending the light of distant objects, a phenomenon that is now one of our primary tools for mapping the dark sector. Zwicky looked at the chaotic motion of a few distant dots of light and deduced the existence of a whole new layer of reality. The modern dark matter era only began when technology finally caught up to Zwicky's intuition. By the 1970s, more precise measurements of galaxy clusters and the rotation of individual spiral galaxies began to show that Zwicky hadn't been wrong. If anything, he had been conservative. The missing mass wasn't an anomaly of the Coma cluster, it was a universal feature of the cosmos. Every cluster we measured, from Virgo to Perseus, showed the same high-velocity swarm that required an invisible gravitational anchor. The footprints were everywhere.
As we reflect on Zwicky's contribution, we see the power of anomalous observation. Most of science is spent refining what we already know, but true breakthroughs come from the people who refuse to ignore the data that doesn't fit the model. Zwicky saw a mismatch between motion and matter, and rather than trying to fix the data to fit the theory, he proposed a new theory that expanded the definition of matter itself. He taught us that the universe is a dark room, and the stars are merely the few candles we have managed to light. To understand the room, we have to account for the shadows. In conclusion, Fritz Zwicky was the original pioneer of the dark universe. He provided the first weight measurement of the unseen architecture, and his missing mass problem remains the central challenge of modern astrophysics. He proved that the cosmos is a heavy place, and that starlight is a poor indicator of true power. In the next chapter, we will move forward to the 1970s to see how Vera Rubin took Zwicky's cluster problem and proved that the same mystery was hiding inside every single galaxy in the sky.
By the late 1960s, the field of astronomy was at a crossroads. While the missing mass problem identified by Fritz Zwicky in the 1930s had lingered in the background of academic discourse, it was largely treated as a cluster-scale anomaly, a strange quirk of the massive, chaotic swarms of galaxies that didn't necessarily impact the physics of individual systems. Most astronomers still operated under the luminous bias, the subconscious assumption that where there is light, there is mass, and where there is darkness, there is nothing. This complacency was shattered by the meticulous, relentless, and revolutionary work of Vera Rubin. Working alongside instrument maker Kent Ford at the Carnegie Institution of Washington, Rubin decided to investigate the internal dynamics of spiral galaxies. Her goal was to create a definitive atlas of how galaxies rotate, but what she found instead was the definitive proof that our understanding of gravity and matter was fundamentally incomplete. To understand the gravity of Rubin's discovery, one must first understand the Keplerian expectation that she set out to verify. Our understanding of orbital mechanics is rooted in the solar system. In our neighborhood, the sun contains 99.8% of the total mass. Because the mass is so centrally concentrated, the planets follow a predictable decline in speed as they move further away. Mercury, the closest planet, screams around the sun at nearly 47 kilometers per second. By the time you reach Neptune, billions of kilometers away, the orbital speed has dropped to a leisurely 5 kilometers per second. This is the inverse square law of gravity in action. As distance increases, the gravitational pull weakens, and the speed required to maintain a stable orbit drops. When Rubin pointed her telescope at the Andromeda Galaxy, M31, every physicist on Earth expected to see this same Keplerian decline. They assumed that because the light of a galaxy is concentrated in its bright, dense core, the stars at the far edge of the spiral arms would be moving much slower than the stars near the center. Rubin utilized a state-of-the-art instrument called the image tube spectrograph. This device allowed her to take the faint light from specific regions of a galaxy and split it into a spectrum. By looking at the H-alpha emission lines of hydrogen gas, she could use the Doppler effect to calculate the precise velocity of that gas. If the gas was moving toward Earth, the light was shifted toward the blue end of the spectrum. If it was moving away, it was shifted toward the red. Rubin and Ford began with Andromeda, painstakingly measuring the velocities of dozens of regions at varying distances from the center. The results were a physical impossibility. As Rubin plotted the data points on a graph, velocity on the vertical axis and distance from the center on the horizontal, the expected curve never appeared. Instead, she saw a flat line. The gas and stars at the very ragged edge of the Andromeda Galaxy, tens of thousands of light-years away from the bulk of the visible stars, were moving at the exact same velocity as the stars near the core. It was as if the inverse square law had simply ceased to exist. In a stable system, a star's orbital speed is a direct reflection of the mass enclosed within its orbit. For these outer stars to be moving so fast without being launched into the intergalactic void, there had to be an enormous amount of invisible mass providing extra gravitational grip.
Rubin did not stop with Andromeda. She knew that a single anomaly could be dismissed as an instrumental error or a unique quirk of one galaxy. Over the next decade, she and Ford observed dozens, then hundreds of spiral galaxies. From the massive, high-luminosity spirals to the small, faint dwarfs, the result was always the same: flat rotation curves. This consistency was the death knell for the idea that the universe was made only of what we could see. Rubin's data proved that every galaxy was not just a disk of stars, but a tiny glowing ember sitting at the center of a gargantuan invisible sphere of mass. This dark matter halo was 5 to 10 times more massive than all the stars, gas, and dust combined. The scientific community's reaction was initially one of profound skepticism. Rubin was a woman in a field that was, at the time, notoriously exclusionary. She was often denied access to the world's most powerful telescopes, such as the Palomar Observatory, which had a no-women policy for its dormitories. Her data challenged the bedrock of Newtonian physics and general relativity. Critics argued that perhaps the gas she was measuring wasn't in a stable orbit, or that the light-to-mass ratio of stars changed drastically at the edges of galaxies. But Rubin was a master of precision. Her observations were so clean and her error bars so small that the missing mass could no longer be explained away as a bookkeeping error. She had moved the dark matter problem from the distant, messy environment of galaxy clusters and placed it right in our backyard. This era marked the birth of the mass-to-light ratio discrepancy. In a typical galaxy, the mass-to-light ratio was found to be far higher than what could be explained by known populations of stars. To account for the rotation curves, astronomers had to propose that the Milky Way and all its neighbors were encased in dark halos that extended far beyond the visible starlight. This realization completely changed our perspective on our place in the cosmos. We were no longer the main characters of the universe. We were the trace contaminants. The normal baryonic matter, the stuff that makes up people, planets, and the periodic table, was revealed to be a tiny minority, a dusting of luminous soot in a universe dominated by an invisible, non-luminous substance. Rubin's work also triggered a fierce debate over the nature of gravity itself. Some physicists, reluctant to invent a new invisible particle, proposed modified Newtonian dynamics, or MOND. They argued that perhaps the formula F equals ma, force equals mass times acceleration, needs a small correction when acceleration is extremely low, such as at the edges of a galaxy. While MOND could explain Rubin's curves with elegant mathematics, it struggled to explain why light bent around empty space, or how the early universe formed. Dark matter, as a physical substance, provided a much more comprehensive solution to the mounting evidence across all scales of the cosmos. The legacy of Vera Rubin is not just the discovery of dark matter, but the elevation of the unseen as a legitimate field of study. She famously said, "Nature has been very clever in hiding the most important part of the universe from us." Her work shifted the focus of cosmology from the study of light to the study of gravity. Today, the Vera Cruz Rubin Observatory in Chile is under construction, tasked with performing the most ambitious dark matter survey in history. It will take 10 years of time-lapse images of the sky, watching how the invisible architecture of the universe pulls and warps the visible world. It is a fitting tribute to the woman who looked at a flat line on a graph and saw the hidden skeleton of the universe. To wrap up this 1,600-word deep dive into the rotation puzzle, we must confront the finality of her evidence. Before Rubin, dark matter was a maybe. After Rubin, it was a must. She proved that galaxies aren't just collections of stars, they are gravitational sinks created by dark matter, where normal matter has simply settled like dust in a corner. As we look at the beautiful spiral of the Milky Way, we must credit Rubin for teaching us that the beauty we see is held together by a dark, silent power that we are only just beginning to name. In the next chapter, we will see how these galactic rotation curves were scaled up into the first supercomputer simulations to see if a universe with dark matter could actually build the cosmic web we see today.